All right, so hello everyone. Thank you for coming here. I'm going to get started. My talk today is going to be about face processing, applying some computer vision principles. So my name is Gabriel Bianconi. Before we get started, I want to talk a little bit about my background. So I'm the founder of Scalar Research, which is a machine learning and data science consulting firm. But also before this, I spent my past several years at the Stanford AI Lab, where I was doing research on deep learning and computer vision. Especially towards the end, I was doing a lot of research on applying computer vision towards healthcare, so interacting with people in this healthcare setting and trying to understand what's going on there. So a lot of the principles I talked about here is some of the things we worked on over there. So I want to basically cover at a high level what is face processing, how computer vision can help us with this, and some of the implications of this field. So today, during this talk, I'm going to cover four main topics. The first one is just a high-level overview of what is face processing, what are some of the tasks people are researching in this field, and so on. Second, I'm going to cover some of the principles of computer imagery and computer vision that can help us motivate why face processing is challenging and why some of the techniques we use are used in this context. And third, I'm going to focus on machine learning and computer vision principles that people are using to tackle the tasks in face processing. And then finally, I'm going to focus on two examples on how we can quickly leverage the things we learned today to come up with interesting examples, interesting prototypes of things we can do here. So let's get started with face processing itself. Face processing is actually a collection of several different tasks, and they are very connected to each other. So the first one and the most common one is face detection. The idea here is that given a picture or a video or something like this, you want to recognize if there's a face in this piece of input and also localize in it. So basically, for example, if you have a picture like this, you want to be able to tell where the faces in this pictures are. And you can see this in a number of different contexts. And the interesting idea behind face detection here is that in itself, it can be pretty useful for a human operator leveraging, let's say, surveillance data or other things like that. But more commonly, it's used as a first level of input for a downstream computer vision task. So if you're doing facial recognition or different sorts of things, you're first going to start with face detection, localize the faces, and using that point in the picture, then you're going to do some more complex analysis and so on. So with this in mind, then we go for a second very common task, which is facial recognition. So the idea here is to identify the faces you've localized in the picture. So we see this in things like this, where we have facial identification. In this case, given a set of faces, we want to identify who this person is. We have something else which can be clustering or similarity search, in which given a number of faces, even though we don't know who those persons are, we want to find similar faces and cluster them together. So this is, for example, what we see in Apple Photos. And we also have facial verification, in which case we want to compare two faces and know if they're the same person or not. So there are some different differences and nuances here. So for example, if you're doing facial identification like on Facebook, you have a large set of faces and you want to find which one it is. But for facial verification, you're just comparing two faces and you're saying yes or no. So depending on the task you're working with and some of the details on the sort of data you have, if you can have any number of faces or a limited number of faces, and so on, the techniques you're going to use is going to change as well. On top of recognition, a common task here is also called facial classification. The idea here is that we want to infer some of the properties about the faces we've localized. So for example, we can look at classifying the gender of the faces. We can try to classify the emotions we see. There's also age estimation. And then we can also look at for a number of other attributes. For example, is this person wearing glasses? Did this person blink while taking the picture? And so on. Another common task we work with is face manipulation. So the idea here is that we want to modify or add pictures to faces. In a consumer setting, a very common example of this is Snapchat filters, where you're deforming the faces, adding objects to faces, and other things like that for entertaining purposes, but there are a number of other uses like that. Those are some of the most common applications of face processing, but we also see this in a number of other settings. So, for example, we also have gaze estimation, where you want to identify where the person is looking at in the picture. You have orientation estimation, where you want to estimate where the position of the face in the 3D space. We have 3D reconstruction, where based on a 2D picture, we want to create a, or multiple 2D pictures sometimes, we want to create a 3D model of a face, and so on. So at a high level, this is some of the many things people are looking at in this field, but so this gives us some context on what we're working on. But before we actually understand how people are tackling those problems, I think it's important to understand how computers represent and manipulate images. So the overall idea here is that images are basically grids of pixels. So if we look at an image like this, we have millions of pixels, and basically we can see the individual pixels here, but the idea is that we have this massive grid of pixels. And each of those pixels is going to be corresponding to a color. Commonly, when we were working with computer vision, we were working with the RGB color model, which stands for red, green, and blue. So each of those pixels is actually composed of 3 colors that we combine to come up with the colors we want to show. So the idea here is pretty similar to the primary color model, where we're combining those colors to create all the colors that we can see on our computer screens and so on. And RGB is one of the common ones, and they can represent a pretty large set of colors, but there are different color models that can be used for different purposes. And the idea here is that depending on how you represent those colors, you can show on the screen different sorts of colors and so on. So when you look at an image, we have this concept that the image is a grid, a 2D grid of pixels, and each pixel is a vector of 3 values here if we're working with RGB. So if we combine that, then we see that an image is a 3D data structure. The idea here is that it has width and height, and each of those pixels also has 3 values. So the idea is that if we think as a matrix or as an array, this is actually going to be called a tensor, which is a generalization of a matrix in 3D. And on a computer science setting for programmers, it's more intuitive to think about this as a nested array, and each of those arrays has a fixed length. And we also then have 3 levels of nested arrays here. So if we're looking at this as a data structure, then basically each image is going to have 3 matrices or 3 2D arrays, one for each of those color channels. So in summary here, we basically have those. For each tensor, we have those 3 values, and then each pixel then is going to have a position for x and y, and then each of those 3 channels is going to have the intensity of that base color. One of the important things to realize here is that the number of parameters we have in an image is actually huge. So if you take a simple iPhone X photo, it's a 12 megapixel camera, which generates an image that's about 4,000 pixels wide and 3,000 pixels long. And if we look at this, then we have 12 million pixels here, and each of those pixels has 3 values. So when we're looking at a single image, we're looking at actually 36 million parameters. So if you're trying to do some machine learning on top of this, in a number of other different settings, you're usually working with a couple dozen or even a couple hundred parameters per sample. Here, each sample is going to have millions and millions of parameters. So this adds a huge layer of complexity, and that's why computer vision has to bring in new techniques to do some machine learning on top of images and so on. So the whole principle here is that when we look at an image, it's very intuitive for us what we're looking at, but for a computer, we're basically going to have 36 million or dozens of millions of parameters like that, and it's hard to actually extract some meaningful representations from those. So this is where machine learning and computer vision comes in. There are usually 2 different lines of thought when it comes to computer vision. Some people look into more the traditional computer vision approaches, and some people are more now focused on deep learning and the more modern machine learning techniques. So the idea in traditional computer vision is that you're going to come up with an algorithm that can extract features which is useful information about the image. Basically, you're going to summarize those 36 million parameters into a small number of very relevant parameters that inform what's going on in the picture. And then you're going to use a machine learning model to make the predictions that you want to work on. And when it comes to deep learning, the main advantage of deep learning is that the model itself learns how to extract those parameters. So you don't have to necessarily say how the model should look at each of the areas of the image and what it should be looking for and so on. Given enough data, the model can learn those things by itself. So I'm going to give an example of a traditional computer vision technique. A very popular one, especially for for facial processing, is called histogram of oriented gradients, or HOG. The idea here is that we can summarize an image by splitting this image in a grid, and for each of those cells, we're going to look at the most common gradients in the colors. So the gradients here are the common directions in the color. So for example, if we have several lines, if you have like an edge or like a boundary in the image there's going to be a very drastic change in the gradients of the colors in that edge. And by knowing where those gradients are, we can basically understand if we have edges, textures, and other things like that. So in a more illustrated way, we have, let's say, the picture of a face. Then we can crop it in several different cells. And for each of those cells, we're going to look at the gradients there and see how common they are. And then for each of those gradients, and usually people are working with the 16 directions of gradients, we can create a vector that represents how common those are. So we can go for a cell that has, let's say, 100 by 100 pixels, which is 10,000 pixels. And again, then this would be 30,000 parameters, and representatives of 16 values, which would be just the directions of the gradients in that cell. So we can go from, let's say, dozens of thousands of parameters to just a couple. And in this way, you can have like a meaningful representation of what's going on and be able to apply some machine learning on top of it. So here's what this looks like in practice. On the left, we have just the gradients for each of the cells in the picture of a face. And then if we do that across thousands of faces and basically average those out, we get the picture on the right. So this picture on the right is representing what a face would look like in general for all those different thousands of gradients. So then once we compare those two pictures, we can see for the overlapping cells, can we tell if they have a high matching rate between the common gradients for what this generic face looks like and the face we're looking at? And then if that's the case, then we can say here is likely to be a face. So if we have like a large image that might have faces in it, we can use the image on the right and basically slide that through the image for like different scales, different resolutions, and so on, in a search for a face in that image. And once we have a match, then we can tell that there's high confidence that we have a face in that region. So more recently, people have stopped using a lot of those techniques and relied more and more on deep learning. The idea behind deep learning is that you have neural networks, which are those models in which you have several layers, and basically each layer is learning more and more abstract features about your input. I'm not going to dive too deep into what's going on, but the idea here is that if you're working with pictures, then we're going to use a variation of this called the convolutional neural network. And the idea is that each of those layers is going to learn more and more abstract representations of the image. So you can think about this such as the first layer is looking for very small lines or edges or things like that. The second layer is going to combine those into having shapes. The third layer is going to combine shapes for more and more complex shapes. And as you go deeper and deeper into the network, you get more and more abstract information until you get to something like faces. And if we try to visualize this, the overall idea is something like this. On the top left, we have this first layer that's going to learn very granular information about the image. This is going to be edges or textures or colors or things like that. As you start combining those on the bottom left, you start to learn curves or other more interesting representations. And then as you start composing those over and over and over again, you start to get more interesting features such as facial landmarks, and then eventually you get to complete faces as well. So a very basic convolutional neural network can learn something like this. One of the drawbacks of using neural networks is that you're going to need massive amounts of data to actually be able to learn this. So when you're using a traditional computer vision algorithm, you're manually specifying how to extract those features. And by doing so, you can actually save the model a lot of the work it needs to do to learn what to actually try to extract. But with neural networks, you're basically telling the model it has to learn how to learn meaningful representations from the images. But to do so, it needs to look at thousands or sometimes millions of images to learn something meaningful. And on top of this, this whole training process can be very slow and very tricky. But one of the main advantages that people are starting to rely on over the past few years is using pre-trained models. So you don't actually have to learn a completely new model from scratch every time. you can start with a pre-existing model for a similar task and then adapt it for whatever you're working on. So for example, if you have a pre-trained model for facial detection, you can actually adapt that or for facial recognition or for classifying emotions or other things like that with way less effort. So this is called transfer learning. And the idea is that by using this, we can apply those concepts to new domains very quickly, and this enables us to iterate very quickly in the field. So I'm going to talk about some of those techniques in practice, and then show a couple examples of how we can implement those things in a useful way. So the first thing we mentioned is that we're going to start usually with face detection. So once we have a picture, we actually have to localize where the face is before we do some more complex analysis there. And to do so, we can use the convolutional neural networks I mentioned and the histogram of gradients and other techniques. I'm going to use the example of a library called face recognition. And we can see that in Python, for example, it's actually very simple to do something like face detection using those pre-trained models I mentioned. So with a library like this, in just 2 lines of code, we can actually load the image and get the coordinates for all the faces using some of those models. And a library like this has several models built in, so we can, with some parameters, you can use the CNNs, you can use HOG, depending on the trade-offs between performance and accuracy and things like that that you want to achieve. And then once you have the face, one of the interesting things we can try to get is something called an embedding. The idea behind an embedding, and this can be applied not just to faces, but to all sorts of data, is that you want to map the data that you have into this coordinate system. For your intuition, you can think about a 3D coordinate system, but usually we're talking about 300 or 1,000 coordinates. And the idea is that in this coordinate system, samples that are similar to each other should be close to each other, and samples that are far from each other should be far from each other. And we can apply this for words, graphs, and also for faces. So the idea here is that we have these coordinate systems, and if we map the image to this coordinate system, the similar faces should be close to each other. And as we're training a model to generate those coordinate systems, the idea is that as it starts looking at pictures, it should bring the 2 similar faces together and 2 dissimilar faces far from each other. And in the context of faces, similar can be a number of different things. We can train the model to extract similar in terms of being the same person, similar for being the same physical characteristic. So for example, we want to cluster by gender, by age, or like different characteristics like that. And then once we have those embeddings, we can actually do a lot on top of them without actually having to rely on the picture itself. So basically, the embedding is a summarized version of what the faces are. And again, with a library like this, we can extract the embeddings for the face very easily using those pre-trained models. And then just using these 2 ideas, we can start to build something useful. So I'm going to use it as an example of Facebook photos. The idea here is that you want to collect the face embeddings from the pictures you know belong to a certain person. So you can do this by looking at their profile pictures or pictures that they've been tagged at before, and so on. And then whenever a user uploads a new picture, you're going to try to detect a face. And once you do so, you can calculate this embedding as well and compare to all the embeddings that you have previously calculated. And basically, you can just compare 2 embeddings by looking at the distance between those 2 points. And if they're above a certain threshold, then you can basically assume that those pictures belong to the same person. And this, at a high level, is how Facebook Photos is doing their recognition. So if we use an example using that library I just showed and just using those 2 lines of codes, this is what we get. If we compute the embeddings and then compute the distances, the distance values between all those people we see that the lowest one belongs to the same person in every case here, and there's a pretty large margin between the different people. Usually also, especially with Facebook photos, if you're working with a closed set of pictures, so for example, you have your friend group or like a number of common pictures that you can compare against, then it's even easier for you to do this thresholding, because you just have to look for the closest one among the ones you have. You don't need to have this arbitrary threshold. So if you can even look for what's the closest one in terms of embedding from all the pictures that we've seen in this person's network and so on. Another useful technique here is called the facial landmarks. The idea behind facial landmarks is that you want to locate key points in the face. So for example, those are going to be eyes, the nose, the mouth, the chin, and other facial pictures like that. In a lot of models, you're sometimes looking for 5 points, sometimes for 50 points, or even more, depending on how much resolution and how much information you want to get. So here's an example with, I think, about 60 points, or the facial features we want to look at. And then using this information, there's a lot of things as well that we can do. We can combine with embedding to have even more information about faces, or we can use those physical coordinates to do things like facial manipulation and so on. And again, this is something that with modern libraries, it's very easy to extract. So with the same library that I've been mentioned, again, in a single line of code, we can extract all the facial landmarks here, and they're going to be clustered by the facial feature, so eyebrows, eyes, and so on. And then we can leverage those to build something like a Snapchat filter. So the idea for a Snapchat filter here is that we want to first localize those landmarks in the face. So when you open your phone camera, Snapchat is running this nonstop, trying to localize where your mouth is, your eyes are, and so on. And then based on that, it's going to place objects on your face. It's going to deform the image you're seeing or do things like this. So we're going to build a very simple example of this. The idea here is that we can first localize like I just showed you, and then once we have those coordinates, we're going to just draw a couple polygons. So here, very crude polygons that we're going to draw on top of the mouth and the eyes and so on. And if we do so with just a couple lines of code, we can have a pretty crude but decent looking filter like this in the case. We start with the picture of the girl on the left. We localize the facial features for her. And then we're basically drawing a semi-transparent red polygon on top of her lips, and then a darker polygon also around her eyes to represent the makeup here. So this is something that with less than 10 lines of code, we could build something like this. And you could do this in real time. It's very performant and so on. And eventually, if you want to build something more complex, you could look at adding shapes or other objects on top of the image. You could look at deforming the face, or applying some more complex techniques to make sure the makeup is not just changing the color, but also blends well with the image and things like that. So when it comes to face processing in practice, there are a number of different ways we can approach this, and there are a number of trade-offs there. So this library I was mentioning, face recognition, it focuses primarily on simplicity. So like I showed you, we can build a lot of examples like Facebook photos and Snapchat filters with just a couple lines of code. And as you go deeper and deeper into the stack, you can have more and more complex libraries that achieve better performance, or they can run faster and things like that. So this is a trade-off that it'll vary depending on the application you're working on and also the stage in the cycle you're at. It's often useful to start with a very simple library like face recognition for a prototype, and once you've proven the concept and you've found the bottlenecks you're working with, you can go look for something that's specialized for whatever task you're working on. And it's also helpful to see that if you're working with face processing at scale, sometimes it's even easier to just use an API. So, for example, most of the cloud providers like Azure and AWS and so on have functionalities for face processing. And for example, with Azure, for $1 or less, you can process over 1,000 pictures. And in doing so, we can, with a single API call, you can localize the faces, you can do recognition, they do classification for a number of common themes from gender to age to a number of physical features and so on. They estimate emotions and so on. So depending on the provider here, you're going to have different functionality, but the idea is that you can implement something like this very quickly using some sort of API like that. So this is what I wanted to cover today. I'm happy to answer any questions you guys might have, and also feel free to reach out if you have any questions. Thank you. I think it's mm-hmm.
How can face recognition software do to know to do the segmentation or know the different zones of a face, such as there is
Okay, so the question was, how can a facial recognition or face detection software detect where where the face is and delimit the boundary of the face, right? Perfect. So yeah, it depends on the technique you're using. So if you're working with some sort of those more traditional computer vision techniques like the HOG I mentioned, you're going to take I showed two examples. Let me pull this up. Um, all right. So on the picture on the right here, we basically have this representation that shows what the average face looks like. And if you overlay this on a face, like the face on the left, then you're going to be able to tell it's a face. When it comes to a large picture that has faces in certain regions, but it's not just like the picture of a face, then what you can do is take the picture on the right and basically slide it through the image. And basically you're going to compute that in every possible region and so on. And you should also do this in terms of like different dimensions of this filter so that you can look for faces that have different sizes and so on. And you can sometimes do this in a pretty simple way. You're just like sliding completely across the face with like several dimensions of this filter, or you can try to do something that has several stages to it. So for example, you can look at just have like a very coarse filter that you're going to apply to come up with some region proposals. And then for those regions that are likely to have a face, then you do something more refined where then you determine if there's actually a face there or not. And you can do something more complex there.
I have another question.
Yeah.
If, for example, the face is turned in some angle, for example, half the face, or how can we detect that? Or, for example, we have some black glasses, sunglasses, sorry. So how can we know the face without direct projection, without flat perspective?
Yeah, so in a lot of cases, when you're creating models like this, you can also have one for different orientations of the face. So one for frontal faces, one for side faces, and so on. And then you're going to use all those different filters to compare and see if you can match any of them. This is the more traditional computer vision approach. In the case of deep learning, then, if you have enough data from like different perspectives, people using glasses or not, and so on, the model itself should be able to learn the representation of a face for all those different variations. So in general, what we see is that techniques like HOG, if you have a frontal face, it works very well. But as you have examples like the one you mentioned, where you have like glasses or occlusion, bad lighting or things like that, then it stops performing that well. And that's when deep learning can be very powerful. And if you have a model that performs very well, then it's able to, by having seen previous examples like that, then it's able to recognize them as well.
I just need some metric because you said for big images, it's a huge amount of data for the training. We need an huge amount of data. And I need to figure out how many photos, for example, we need to make a classifier between female and male. And how deep will be the CNN, for example, how many neuron or how many layer we need, and how many time it will take to train the model. I need just some metric about it, you know.
Yeah. So some of the things you can leverage to reduce the needs for something like that is to rely on a pre-trained model. So for example, a lot of the existing face processing models.
I don't want to reduce, I want to know how many, in average, it takes to train it. How many images, how many time, how many layers.
Yeah, so for a regular, let's say, face detection or recognition model, a lot of the data sets have in the order of like 1 million faces. Or like 100,000 faces, so that order of magnitude. But then using the data set, even if it's not explicit for, let's say, I think you mentioned gender classification, you can train a model for a different task that's related to face processing using this large data set. And then you can use a much smaller data set for your specific task and just fine tune the model. So then you can go for, let's say, in the thousands of examples or something like this. And then also if you work with, let's say, embeddings or things like that I mentioned, you can also train the whole model like a very deep CNN. And usually in those cases, you're working with, let's say, 50 to 100 layers or something, sometimes even deeper. use that to generate embeddings, and then you can have a very simple model go from the embeddings to learn to classify the embeddings into the gender and so on. So if you're going to do this from scratch, then it's going to be a substantial task. So for example, just to give you some examples, for like state-of-the-art face detection, I think it's a network that has like 150 layers. It's a ResNet 152 backbone on top of like some variations here. State-of-the-art for detection, for recognition is also going to, it's what they call like a, what's the name? Basically 2 sibling networks for each of the images. And again, those are super deep in both data sets. They're looking between in the range of like 1 million images. But then again, after you learn this and you can leverage this pre-existing research, you can do something with like way less computing power and way less data.
So question, so when you use facial unlock on say an Android or iPhone, what kind of, is that using neural networks or is that using more the old techniques for facial recognition? Because obviously you need it to process very quickly, right? So I was wondering which.
I'm actually not sure what they're doing in practice there. I know some of the differences that they have, at least on the iPhone, I'm not sure about Android, is that on top of the RGB image you have, they also are capturing the depth. So they have a depth sensor that can basically create like a simple 3D model of your face. And then they combine that information with the image from the camera to actually try to recognize. And this can help, especially for in the context of verification here, where you're comparing 2 faces. And you have this need for high security, so you can make a lot of mistakes here. That helps a lot. But I'm not sure exactly which model they're using under the hood there.
Okay. So you have a consultancy firm, right?
Mm-hmm.
So the companies that ask for your services, right? Do they pose ethical questions about this kind of technology?
Yeah. So in the case of face processing, that's why it's like a lot of the AI challenges we work with. In a lot of cases, there can be problems, let's say, biases in the data set where it's going to discriminate against people. This can be used for purposes like surveillance, which can be both good and bad depending on how it's applied and so on. In the case of the companies I've worked with, a lot of the cases were used for internal purposes. So I haven't come across like a very large ethical dilemma here yet. I try to make sure I'm working with companies that are doing this in a responsible way. So for example, some of the projects I've worked on was for physical security inside of like manufacturing plants and warehouses and things like that, which are in like a private space for controlled people, for like employees and things like that, and not looking at like, let's say, the general public in like a public space or like in a store, in a mall and so on, in which I see then more as an ethical problem rather than like looking at your private space, be it like at your home, at your office or something like that.
No questions? Thank you.
Thank you.